What happens when something from the darkest depths of the universe begins to behave in ways that no scientist on Earth expected? Tonight, friends, stay until the end, because what is happening in our sky could forever change the way we understand the cosmos. Just a few weeks ago, a telescope located in the heart of Mexico City captured something extraordinary, something that has astronomers around the world awake at night, searching for answers that seem to slip through their fingers like fine sand.
Good evening, dear listeners. Felipe Suarez here, accompanying you on this starry night. Have you ever thrown a stone into the air and expected it to change course on its own? Because that, in essence, is what we are witnessing with this cosmic visitor called 3I Atlas. And I know it sounds impossible, I know it seems like something out of a science fiction movie, but the data is there, the images do not lie. What will happen when this object reaches the vicinity of Jupiter in 3 years? Join me to find out.
The Comet 3. I Atlas is not an ordinary visitor. It was not born in our solar system. It did not form in the Oort cloud or in the Kuiper belt, those icy regions that harbor the comets we have known for centuries. This object traveled distances that the human mind can barely conceive, crossing the void between the stars for millions, perhaps billions of years, until it finally arrived in our cosmic neighborhood. And from the moment it was first detected, it began to show behaviors that defy everything we thought we knew about comets and about the laws that govern the movement of celestial bodies. The most recent images, captured by a team of astronomers working tirelessly in Mexico City, revealed something that left the scientific community in a state close to astonishment, mixed with a deep unease that few dare to admit publicly. The trajectory of this comet, according to the most precise calculations available, experienced an adjustment. Not a chaotic deviation caused by random forces, not a casual push from the solar wind, as happens with so many other objects that traverse space. It was a precise change, almost millimetric in astronomical terms, that placed it on a direct encounter route with Jupiter's Hill radius. To understand the magnitude of this finding, one must first understand exactly what the Hill radius is. Imagine an invisible zone around any massive planet, a subtle boundary where that world's gravity begins to dominate over that of the Sun. It is like its own territory, a gravitational kingdom that separates a planet's influence from the influence of our parent star. Jupiter, being the undisputed giant of our system, possesses an enormous Hill radius that extends for more than 53 million kilometers in all directions. It is a region of space so vast that it could contain Earth hundreds of times without the slightest problem. And 3I Atlas, after that mysterious adjustment in its trajectory, is heading exactly toward that edge. Not near it, not in its general proximity, but exactly toward it. The precision is of the type that makes astronomers stop what they are doing, review their calculations 2 and 3 times, and then look for errors that simply are not there. It is the type of precision that defies statistical probabilities in a way that is profoundly uncomfortable for those who prefer simple and conventional explanations. But here comes the part that truly keeps those who study these phenomena with dedication and rigor awake at night. That adjustment did not occur when we could observe it. It happened when the comet was behind the Sun, completely invisible from Earth, beyond the reach of any terrestrial or space telescope. It was as if the universe had deliberately decided to hide the exact moment when something extraordinary happened. When the object finally reappeared in our field of vision and scientists updated their orbital models with the new data, they discovered that something, whatever it was, had pushed the comet just enough to radically change its destiny. The odds of this happening by pure chance are astronomically low. We are talking about 1 in a billion, perhaps worse. It is like throwing a dart from 100 meters away, blindfolded, in the middle of a windstorm, and still hitting the exact center of the target. That is exactly what this interstellar visitor has just accomplished, and no one can explain how it did it.
Do you realize what this means, my friends? We thought a comet was simply a ball of ice drifting along. following the laws of gravity like any other object in space. But 3i Atlas is telling us that maybe it is not that simple. What kind of natural force can produce that level of precision? Is there something we are not seeing, something our instruments cannot detect yet? I promise you that the further we go into this story, the more fascinating it gets.
When a celestial object changes course unexpectedly, scientists look for explanations within the framework of known physics. It is the natural procedure, the path that science has traveled for centuries to understand the mysteries of the universe. The first candidate, the most obvious and studied, is outgassing. Comets are composed mainly of ice, dust, and volatile compounds that sublimate when they approach the sun. Those jets of gas act like small rocket engines, pushing the comet in directions that may seem unpredictable, but that follow identifiable patterns when analyzed in sufficient detail. It is a well-documented phenomenon, observed in dozens of comets over decades of meticulous study. Astronomers have developed sophisticated mathematical models that can predict with reasonable precision how outgassing will affect the trajectory of a given comet. But here is the fundamental problem with that explanation when we try to apply it to 3i Atlas. Outgassing produces chaotic pushes, not precise adjustments. It is like trying to park a car by blowing on it with an industrial fan. You could move it, without a doubt, but you would never place it perfectly in the designated space, aligned to the millimeter with the lines painted on the ground. And yet, that is exactly what seems to have happened with 3i Atlas. The push was of the exact magnitude at the exact moment to place it on a trajectory that will culminate in March of the year 2026 with a close encounter at the gravitational boundary of Jupiter. It is the type of coincidence that makes even the most skeptical scientists begin to scratch their heads with genuine perplexity, searching for alternative explanations that simply do not appear. The images captured from Mexico City also reveal another intriguing element, something that adds an additional layer of mystery to this cosmic enigma that grows with each new observation. 3i Atlas not only changed its course inexplicably, it is also exhibiting a completely anomalous tail structure that defies models established over decades of cometary research. Comets, as many know, develop spectacular tails when they approach the sun. Solar radiation and stellar wind push dust and gas away from the nucleus, creating those luminous trails that have fascinated humanity since time immemorial. Our ancestors saw them as omens, as divine messages written in the night sky. Today, we know they are perfectly natural physical phenomena, the result of the interaction between cometary material and the energy of our star. But 3i Atlas has something that very few comets show, something that has puzzled observers since the first weeks of intensive tracking. An anti-tail, a tail that points toward the sun, not away from it. This phenomenon, although rare, is not completely unknown in cometary astronomy. It occurs when heavy particles remain suspended along the comet's orbit, and from a certain observation angle they appear to form a tail that defies apparent logic. It is a perspective effect, nothing more, or at least that is what it should be, according to all the models we have developed.
But here comes what has me truly fascinated, friends. The anti-tail of 3i Atlas is too narrow, too defined, too stable. Do you know what it looks like? It looks as if someone had drawn a straight line with a laser across millions of kilometers of empty space, and that according to the physical models we have, simply should not be possible. Are you starting to understand why this object has everyone so unsettled?
When a comet releases dust into space, that dust should disperse in a predictable manner. The sun's gravity, the constant pressure of solar radiation, the small gravitational perturbations caused by nearby and distant planets. Everything contributes to the particles spreading in a broad and diffuse pattern over time. It is basic physics, celestial mechanics that we have understood and used to predict the behavior of countless objects for more than 3 centuries of rigorous astronomical observation. But the anti-tail of 3i Atlas does not behave that way. It looks ordered, it looks intentional, it looks as if something were keeping those particles in perfect formation across distances that defy human imagination. And that raises a profoundly uncomfortable question for the scientific community, a question that many prefer to avoid, but that becomes inevitable when the data is analyzed honestly. What natural force can maintain such a precise structure across such vast scales? Astronomers have proposed several theories to try to explain this anomaly, working day and night to find answers that satisfy the demands of the scientific method. Perhaps the comet's composition is completely unusual, with types of ice that sublimate in ways that our models do not yet correctly capture. Perhaps magnetic fields are involved, electromagnetic interactions between the cometary dust and the solar wind that our equations still do not describe with sufficient precision. Perhaps the internal structure of the nucleus is so irregular, so different from any comet we have studied before, that it produces perfectly directed gas jets that create apparently artificial patterns, but that in reality obey natural processes we simply do not understand yet. All of those are possible explanations. Scientists are working with every available piece of data, every captured image, every spectroscopic measurement, but here is the fundamental problem that none of these theories can completely solve. None of those explanations fits perfectly with all the observations. Every time it seems that a theory works to explain one aspect of 3I Atlas's behavior, a new detail appears that does not fit, a piece of the puzzle that simply does not match the rest of the picture. Observations made in recent weeks have revealed significant changes in the color of the coma surrounding the comet's nucleus. Before perihelion, that point of closest approach to the Sun, the coma showed a characteristic reddish hue. But approximately 4 weeks after perihelion, images obtained by a large telescope 8 meters in diameter began to show the halo with a distinctive green coloration. This color change is not a minor detail, nor a curiosity without importance. The green tone is a strong indicator of the presence of molecules such as diatomic carbon, which emits light in that specific range of the electromagnetic spectrum. In practical terms, this means that the molecular composition of the coma changed after passing through the intense heat near our parent star. This type of change implies chemical and dynamic processes occurring at scales that still need to be measured and fully understood.
Had you ever thought that a comet could change color like that, as if it were a cosmic chameleon? Me neither. And there is something else that does not let me sleep peacefully. Space instruments sensitive to X-rays detected a glow coming from the region around Atlas. The extension and spatial distribution of that emission are greater than expected for a typical comet with similar visual appearance. What is really happening up there, friends?
Another relevant point that has captured the attention of the most meticulous researchers is the X-ray emission associated with the interaction with the solar wind. Space instruments sensitive to this wavelength observed brightness coming from the region around 3I Atlas. The most plausible mechanism, already studied in other comets, involves the interaction between the solar wind and the gases released by the coma, which generates emission in this particular energy range. What stands out here is not simply the existence of X-rays, something that has been observed in other comets before, but the observed extent of this glow. According to data published by various research teams, the range and spatial distribution of the X-ray emission are considerably greater than expected for a typical comet with similar visual appearance. It is as if the object were radiating energy at scales that exceed the predictions of our current models. There is also the issue of visual scale. Recent images cover enormous regions around 3I Atlas, spanning from hundreds of thousands to millions of kilometers. This provides an important physical context that should not be overlooked. The structures observed are not local details, nor small irregularities that could be attributed to photography or data processing effects. They are massive features that occupy volumes comparable to the largest interplanetary systems we know. When we talk about plumes and jets extending millions of kilometers into space, we are not dealing with small surface variations. We are facing phenomena that require considerable sources of energy and mass. sources that our current models have difficulty explaining satisfactorily. The distribution of dust around 3I Atlas presents another mystery that has the most experienced specialists perplexed. In a typical comet, we expect to see a clear separation between fine particles and coarse particles. Fine dust, being light, is quickly pushed away from the nucleus by the pressure of solar radiation. Coarse dust, being heavier, remains closer to the original orbital trajectory. Over time, this separation becomes very evident in observations, allowing astronomers to clearly distinguish between different types of material. But in 3I Atlas, this separation is not as clear as it should be. There are regions where fine dust and coarse dust appear homogeneously mixed, as if they had been released at the same time from the same region of the nucleus, but then behaved in completely different ways than expected. It is a pattern that defies our models of cometary dust emission in fundamental ways that force researchers to rethink assumptions they had taken for granted for decades.
And when I say it does not fit, my friends, I am not talking about small discrepancies that we can adjust with a bit of advanced mathematics. I am talking about differences that force us to reconsider our most basic assumptions about how these objects work. Could 3I Atlas be made of materials we have never seen before? Does it come from an environment so different from ours that its physical processes bear no resemblance to what we know? Think about it for a moment.
That possibility is very real and deserves serious consideration by the entire international scientific community. 3I Atlas is an interstellar object, which means it formed somewhere completely outside our solar system, perhaps around a star very different from the Sun, a cold red dwarf whose light barely warms the planets that orbit it, or a blazing blue giant whose intense radiation creates conditions that do not exist anywhere in our cosmic neighborhood. Perhaps it formed in a region of the galaxy where the conditions of temperature, pressure, and chemical composition were radically different from those that existed in the primordial nebula that gave rise to our own solar system approximately 4,500,000,000 years ago. If that is the case, then the comet could contain types of ice that we have never had the opportunity to study directly. Organic compounds that do not exist on Earth or in any local asteroid or comet. Crystalline structures that sublimate in completely unexpected ways when heated by the light of our star. All of that could explain, at least in part, why the behavior of 3I Atlas is so puzzling for our current models. But even accepting those extraordinary possibilities, the problem of precision still remains. We still have to explain how a supposedly natural object could adjust its trajectory with such precision that it will end up passing through Jupiter's Hill radius in the year 2026. And that, honestly, is the hardest part to accept. Not because it is physically impossible, but because it requires such a specific combination of factors, so statistically improbable, that it almost seems designed by some intelligence capable of calculating trajectories across distances and times that surpass anything humans have ever attempted. Jupiter's Hill radius is an immense region of space with a radius of more than 53 million kilometers. It is a zone where the giant planet's gravity begins to dominate over the gravitational influence of the Sun. For an object traveling through interstellar space at tremendous speeds, arriving exactly at that edge has no obvious purpose from a purely physical standpoint. It is not a place where something special happens naturally, like a breakup from tidal forces or a sudden thermal activation. It is not an orbital resonance point that could capture the object and turn it into a new permanent member of our system. It is simply a gravitational boundary, an invisible frontier in the void of space. And yet, 3I Atlas is heading directly toward it with a precision that is almost disturbing for those who analyze the data carefully.
I constantly wonder, friends, if this were a coincidence, it would be one of the most extraordinary coincidences in all of modern astronomy history. But if it is not a coincidence, if there is a reason why this interstellar visitor is heading toward that specific point in space, then we have to ask ourselves, what is that reason? Is there something in Jupiter's Hill radius that we are not seeing, something our instruments do not detect?
The possibility that the comet's trajectory was determined long ago, perhaps even before it entered our solar system, is speculative without a doubt. But it is not completely far-fetched when considered within the appropriate context and with the open mind that genuine science requires. If 3I Atlas were an artificial object, or at least an object whose movement had been influenced by some type of technology at some point during its long journey through interstellar space, then its trajectory could have been planned in advance. It could have been specifically designed to perform a flyby of Jupiter, perhaps to use the planet's immense gravity as a gravitational boost, a cosmic slingshot that would accelerate it upon its exit from the solar system toward a new destination among the distant stars. It is a maneuver that our own space probes have performed dozens of times with resounding success. Voyager 1 and Voyager 2, those ambassadors of humanity that now navigate through interstellar space, carrying messages from our world to whoever may find them someday, used Jupiter precisely for that purpose more than 4 decades ago. And if an extraterrestrial civilization wanted to send an exploration probe across the galaxy, using giant planets like Jupiter to adjust trajectories and gain speed would be a perfectly logical and extremely energy-efficient strategy. Professor Abraham Loeb of Harvard University is one of the most prominent and also most controversial voices in this type of debate that mixes rigorous astronomy with questions that many would prefer to avoid. He is not a fringe theorist nor an attention seeker chasing sensationalist headlines. He is a genuinely respected scientist with hundreds of publications in the world's most prestigious scientific journals. Someone who led the Harvard Department of Astronomy for nearly a full decade. And he has suggested something that makes many of his colleagues feel deeply uncomfortable. Loeb argues that objects like 3I Atlas, and before it the famous Oumuamua, might not be completely natural in their origin or in their current behavior. He is not categorically stating that they are alien spacecraft. He is not saying that there are beings from other worlds piloting them through the cosmos. What he is saying, with the caution proper to a rigorous scientist, is that the anomalies we are observing are so significant, so difficult to explain satisfactorily with known physics, that it would be scientifically irresponsible not to consider all possibilities. And that includes, however remote the probability may seem, the possibility that we are observing something out of the ordinary, something that could include technology of unknown origin.
Look, friends, I know perfectly well that sounds like science fiction, I know, but if Loeb is asking these questions from Harvard's professorship, and more scientists are starting to admit, even if only in private conversations, that there is something genuinely strange with these interstellar visitors, then maybe we should also keep an open mind. Do you not think so? Do you remember Oumuamua?
Oumuamua, that elongated object that passed through our system in the year 2017, was the first of these visitors to be detected. It appeared without warning in October of that year, captured by the Pan-STARRS telescope located in the volcanic heights of Hawaii. Its name, in the Hawaiian language, means approximately messenger from afar arriving first, and it was a truly strange messenger, without the slightest doubt. Its shape was completely unusual for any known cosmic object, elongated like a giant cigar, perhaps 10 times longer than wide, a proportion that had never been observed in any asteroid or comet in our solar system. It showed no visible tail, despite having passed relatively close to the sun, something unexpected if it really was a traditional comet with ices that should have evaporated under the solar heat. And most puzzling of all, it accelerated as it moved away from our star, as if something invisible were pushing it outward. Astronomers proposed multiple explanations for that anomalous behavior. Outgassing of exotic ices that did not produce a visible tail. Solar radiation pressure, acting on an unusually reflective and thin surface. Complex thermal effects that no one had previously considered, but no explanation fit perfectly with all available observations. Each theory left some loose end, some unresolved detail that troubled the most meticulous researchers. And then, before we could study it more thoroughly, with more powerful instruments, Oumuamua disappeared into the darkness of interstellar space, moving away from us at tremendous speeds, leaving us with more questions than answers and a persistent feeling of lost opportunity that still pains those who devoted entire weeks to trying to understand its nature. And now we have 3I Atlas, another interstellar visitor, another object that behaves in ways that defy our established expectations. And this time, the situation is different. This time, the object is not yet moving away. This time, we have years ahead to study it, to observe it with every available instrument, to try to truly understand what is happening. Loeb and his collaborators have approached the most recent data from 3 main lines of reasoning that deserve careful consideration. The first concerns the change in composition. The transition from red to green is consistent with the activation of different molecules near our parent star, especially with the presence of diatomic carbon in the post-perihelion period. This indicates that the coma contains variable components and that heating significantly alters the chemistry of the observed emission. The second line involves X-rays and their anomalous extent. While X-ray emission is expected when there is interaction with the solar wind, the observed intensity and extent raise important questions that do not have easy answers. The central problem is that the amount of gas required and its spatial distribution seem incompatible with the estimated size of the nucleus. If we assume conventional cometry behavior, the numbers simply do not add up. The third line deals with the real and persistent antitail. The antitail of 3I Atlas cannot be attributed to a simple geometric perspective effect. Images obtained over time show that it consistently points toward the Sun at different times and from different positions of Earth. For Loeb, this demands direct physical explanations, whether through ice fragments released from the side facing the star or through collective dynamics caused by non-gravitational acceleration.
Will it be enough time to solve the mystery, friends, or will it leave us with even more questions than we already have? The truth is that no one can know for certain at this moment, but what we do know is that every passing day, every new image captured, every new measurement made, brings us a little closer to the truth. And that, by itself, is already extraordinary. Does it not seem exciting to you to be witnesses of this?
These lines of explanation are not mutually exclusive. They reveal different facets of the same enigma that has captured the attention of the global astronomical community. Mass and energy being ejected in a non-trivial manner, with a geometry that defies the intuition built from the typical behavior of known comets that we have studied for centuries. In comets from our system, the presence of an antitail can usually be explained by a geometric projection effect when Earth crosses the comet's orbital plane. In the case of 3I Atlas, the antitail appears in images obtained under geometric configurations, in which this effect can be safely ruled out. This means we are not dealing with an optical illusion, but with a real emission that points toward our parent star. The paradox arises because the basic physics of dust and gas predicts that both radiation and solar wind push particles away from the star. Thus, observing a luminous plume directed toward the star requires an explanation that goes beyond the standard understanding we have developed over decades of rigorous cometry study. Among the possibilities that scientists are considering are the massive release of extremely small fragments that evaporate quickly before being pushed away, or the existence of a localized dynamic flow that actively directs material toward the star. It has also been proposed that a swarm of objects or particles could lag behind the main trajectory due to non-gravitational acceleration of the main body, creating a collective effect that manifests as a plume directed toward the star. Another hypothesis involves complex sublimation processes with atypical composition dominated by gases such as carbon monoxide and carbon dioxide, with little water, altering the dynamic response of particles to solar radiation in ways we have not observed before. Each of these hypotheses solves part of the problem, but none manages to simultaneously explain the color change, the X-ray emission, the observed scale, and the persistence of the antitail without resorting to assumptions that are still poorly tested. This is exactly the point emphasized by Loeb. Recognizing the anomaly is the first step toward advancing scientific knowledge. The images obtained from the telescope in Mexico City are contributing crucially to this international scientific effort. The clarity of the photographs, the resolution achieved, the ability to capture fine details in the tails and in the enigmatic antitail. All of this is allowing researchers around the world to build an increasingly complete model of what is really happening with this cosmic visitor.
And what they are observing is absolutely fascinating, my friends. The tails of 3I Atlas are not static structures, as might be expected from a simple piece of ice and rock adrift. They are constantly evolving, changing shape, developing new structures almost in real time before the astonished eyes of observers. Have you ever heard anything like this? Me neither, until now.
There are specific moments when the antitail intensifies dramatically, becoming brighter and more defined than any model predicts. There are moments when new secondary tails seem to sprout from the nucleus, like branches of a cosmic tree growing at impossible speeds. It is as if the comet were somehow alive, breathing, reacting to changing conditions as it travels through our solar system toward its encounter with Jupiter. Normal comets, of course, also show changes in their activity over time, but generally those changes are predictable. They are clearly correlated with the distance to the Sun, with the rotation of the nucleus on its own axis, with the orbital geometry that determines how much solar radiation they receive at each moment. They are changes that our models can anticipate with reasonable precision based on decades of observation and analysis. With 3I Atlas, the changes seem to occur without a clear reason or an identifiable pattern. It is as if the comet were responding to signals we cannot detect with our current instruments, reacting to invisible stimuli that escape our present understanding. One of the aspects that has generated the most intrigue in the scientific community is the variability of the object's brightness. Astronomers are documenting fluctuations that do not correlate cleanly with the expected rotation of the cometary nucleus. The light curve, that record of how brightness changes over time, shows irregularities that suggest an extremely complex shape of the nucleus, or emission processes that vary in ways that our current models cannot satisfactorily reproduce. The public reaction to these discoveries has been immediate and intense. In live broadcasts and on social media, severe criticisms have emerged toward the agencies that published the images. Some people even accused the official images of manipulation or charlatanism. There has also been distrust regarding the successive adjustments of orbital parameters published by official organizations. Among the most repeated points in the public debate are issues that deserve scientific attention more than polarization. One of them is the difference between raw data and processed images, since adjustments in contrast, filters, and mosaics can alter the perception of the color and extent of the observed structures. Another point is the successive corrections of orbital parameters, which are normal but should be accompanied by clear documentation of methods and uncertainties. There are also disputes about composition, with observers noting that some reports avoid direct statements about certain elements, limiting themselves to interpretations, which generates distrust when data is not open and accessible for independent verification.
It is as if 3I Atlas were playing with us, friends, revealing clues here and there, but never showing the complete picture. And that is precisely the frustrating, but also fascinating part of all this. Every time we think we are close to a definitive answer, a new piece of data appears that complicates everything. Will we ever come to fully understand it? That is what we all ask ourselves every night looking at the stars.
This public criticism serves as a reminder that scientists and observatories need to publish not only the final images, but also the initial data and processing steps. Only then can the debate move from speculation to the realm of empirical verification that characterizes genuine science. When accumulated observations do not fit existing models, there are three possible paths. The first is to look for instrumental or processing errors. The second is to adjust physical models with testable hypotheses. The third is to consider bolder alternatives if previous hypotheses fail. The problem arises when one jumps directly from searching for errors to final declarations without going through the complete testing process. Loeb makes clear that recognizing anomalies is not a scientific weakness, but the starting point for learning. He does not demand definitive conclusions, but rather that the data be analyzed without forcing it to fit a prior narrative. This is the stance that should be demanded. More open data, more independent replication, and fewer attempts to prematurely close the debate. To advance in understanding 3I Atlas, three coordinated research fronts are required. The first is the publication of raw data, including original images, metadata, and all reduction steps. The second is intensive multi-band monitoring with coordinated campaigns in optical, infrared, ultraviolet, and X-rays to map composition, temporal variations, and dynamic structure. The third is physical modeling with testable hypotheses, such as quantifying whether a large amount of micronized ice particles can explain the antitail without violating energy limits, or whether it is necessary to include non-gravitational acceleration of still unknown origin. Additionally, statistical comparisons with archives of interstellar objects and comets from our system are essential. If similar sets of anomalies are extremely rare or non-existent, this indicates a turning point in astronomical knowledge. The list of known anomalies of 3I Atlas is truly impressive when considered as a whole. First, retrograde trajectory aligned with the ecliptic. Second, jets pointing toward our parent star. Third, a nucleus with anomalous mass. Fourth, an articulated arrival window involving Mars, Venus, and Jupiter. Fifth, a coma enriched in nickel. Sixth, gaseous emission with water scarcity. Seventh, strongly negative optical polarization. Eighth, arrival direction coinciding with the region of the so-called wow signal. Ninth, sudden brightness increases with bluish tone. 10th, severe energy discrepancy. 11th, non-gravitational acceleration without a compatible cloud of ejected material. 12th, extremely collimated and persistent jets.
Over the coming weeks and months, friends, more data will continue arriving from observatories around the world. More analyses will be published in scientific journals. More researchers will offer their interpretations of what is really happening up there. Does it not excite you to be able to follow this story alongside us? Because for me, honestly, it keeps me awake at night.